I'm Valerie Pascarella. I am a research scientist here at Google with the machine learning data products team, and we are super excited to be here today to talk about Cloud Score Plus. I'm also joined by my colleague here.
Hello, everyone. Good afternoon. My name is Andrea Nicolau. I'm a geospatial data scientist with the Spatial Informatics Group and the Servia Masonia Hub.
Yeah, and Andrea is also a GDE with the Earth Engine team. So, all right.
Yep.
Well,
See you in a bit.
I'm going to be kicking us off here today, but before we get into our agenda, I wanted to explain a little bit about why we did Cloud Score Plus. Hopefully you saw Rebecca's keynote the other day. Did everybody see Rebecca introduce? Yeah, awesome. So you have a little bit of a taste of what we're going to be doing. So as you may know, we are also the producers of the Dynamic World dataset. So when it comes to Sentinel-2 and cloud, shadows, all sorts of atmospheric artifacts, we felt your pain. So we definitely know there are lots of instances where no matter what you do, how many different algorithms, data products you throw at the imagery, you still might end up with things like the images we see on the right there, where the dynamic world predictions, we've got mist clouds that are causing misclassifications, we've got lots of missing data where we've tried to smudge out the shadows. And so we were thinking a lot about how do we make Sentinel-2 data or optical imagery in general more usable, keep more good pixels, make a more flexible solution. And if you were here last year, you might have been part of the very small set of folks who joined us for our Cloud Masking Unconference, and we heard the same story we'd been experiencing ourselves, that this is an ongoing struggle, again, especially for Sentinel-2 data. So we are really excited to be back this year with a solution in hand. So the first time I saw this imagery, my first thought, Sentinel-2, like you've never seen it before. This is, I mean, almost looks 3D. It's so crisp and clean. And this is 1 year of Sentinel-2 RGB data for the Western United States, median composite. And we have successfully removed the clouds, the shadows, all of that noise, and gotten this beautiful, beautiful, clear image. And I'm going to start with this code snippet. There is a short link down at the bottom there if you want to reproduce this. We'll have a code editor example soon to show you a bit more about using Cloud Score Plus, but I want to start with this, and we're going to keep coming back to this. It is this simple. It's not a lot of Earth Engine code to make a composite. If you've had to deal with other cloud removal products or even bit masks, you're used to having lots and lots of lines of code just to get those clear pixels. It's going to be easier than ever. I'll tell you more about why soon. I should mention as well, the link to these slides is over on the top of the board here. We've got a link, I actually had it in the first slide as well, where G4G'23 Cloud Score Plus. And again, that code snippet is at the short link if you want to access it at any time. So what are we talking about in this session today? So we are going to go through a few different phases of this process. We're going to start with how the Cloud Score Plus model is trained, how it thinks about detecting clouds, really our own process of discovery here, and how to build a better cloud and shadow detection approach. We're going to go through a model overview. A lot of you came to visit us at the demo station yesterday, had questions about the model itself. It is a deep learning approach. So we're going to tell you a little bit more about what's under the hood. Then we're going to get into the specifics of the data products and this awesome new function we have that makes working with the Cloud Score Plus collection easier than ever. So what we're really launching today here at G4G. And then Andrea's going to come back up. She has piloted using Cloud Score Plus for an awesome land cover and land use classification. I'm going to show you more about, how you're going to think about using this in practice, lots of the options. She's done some great analysis using the data set itself. And at the end, we'll get into just some hands-on working with the data, looking at the data. Again, if you stopped by our demo booth last night, you got a sneak peek, but today you'll have the links to our apps, tools, and again, that code, a couple of code snippets to get you started. So, learning to detect clouds. It's not as easy as one might think, but let's start instead with a simpler exercise. We're going to see this image up here. It's a Sentinel-2 image of the area we are in today, right over Mountain View, California. And if I showed you this image, and I show you this image, raise your hand if you think these are the same location. Maybe. But looking at the two, okay, so maybe. What if I show you back to that first image again, and I flash to this image? Are these two the same location? I'll flash back and forth. A, B. Raise your hand if you think they're the same location. Now, how did you know? Because, right, in the first image, you might say, all right, well, the colors are different. The things just, they look different. I get the sense that these are not the same place. Well, if I go forward again here and flash back and forth, I'm seeing some changing colors, especially if I look up in these wetland areas in the bay. But your brain knows a lot of that stuff has stayed the same. So this is a key point of how we developed our models. Let's keep going further, though. If I look at this image compared to the previous, are these the same location? Yeah. Got these big intruders coming in. I'm seeing some differences, but yet again, my brain is telling me, well, there's enough of this the same that I'm judging that it's probably the same. What about this one? Do you think these two are of the same location? Hands up. All right, we're still pretty convinced. There's not a lot showing there. I mean, how are we doing it? We're using as much context as we have, and if it's me, I'm thinking about that one little patch, and when I flip back and forth, it seems to be the same place. What about this one? How many people feel confident this is the same location? Yeah, I'm seeing lots of the shruggy face. Now I'm a little less clear. You might peek down at this bottom corner and go back and forth and maybe convince yourself, but that's a tough one. How about here? Not so much, right? Totally obscured, we've got clouds. And so this is how we actually started thinking about the way we built our model. And again, I'll get more into what we did exactly under the hood. But we have these kind of three tenets that underlie the CloudScore Plus approach in general. And that's when we have a relatively clear location or a relatively clear image of the same location, they look very much the same. There's a lot of similarities in the spatial features, in the colors, and we can tell that those relatively clear things came from the same place. And if we understand that images are from the place, we actually had to understand something about what wasn't on the ground, right? When I showed those images of the clouds, you were like, well, that's not telling me I moved location. That's just telling me that there's clouds in the image. So your big neural net on your shoulders is able to sort out that if you've got these images with or without clouds, that there's some understanding of what's in the atmosphere versus what's on the ground. And then finally, the other piece of this whole puzzle is that traditionally cloud masks have been approached as a classification problem or a segmentation problem, where you want to take all the pixels and group them. I want to say, these are the clouds, these are the shadows. And it feels really simple until you start looking at things like this and realize that the edge of a cloud, tell me where the cloud stops. I can tell you when I'm in the middle of it. I can tell you when I'm looking at clear ground, but that kind of transition zone where you can partially see through some of these clouds, especially like high, thin cirrus, I'm still seeing the ground. So is it a cloud? Is it ground? Well, it's actually a continuous phenomenon. So why are we trying to bin everything into discrete labels? And so if you've seen anything with CloudScore Plus so far, it's actually a continuous score that works to define whether or not a pixel is totally clear, so it gets a score of 1, versus totally occluded, gets a score of 0, those images where you just absolutely cannot see through to the ground. So if we started by looking at images and thinking about how we process, how do we formalize this into a machine learning model? Well, we used an approach, we actually have two models involved, where we relied on this increasing specificity that I just walked through with examples here. So if you can tell that two images are from the same place, like we were doing when we were looking at those snippets, then you can tell which differences really matter when you're thinking about detecting an atmospheric occlusion, either a cloud or a shadow. And so if you understand those semantics, hey, this is what's clear and on the ground, and I really want to keep those pixels versus what's being occluded, then you can tell exactly that, what's on the surface and what's the occluder, and that's what gets us to CloudScore Plus as a data product. And if we take this kind of increasing specificity approach, now I'm going to bring in some of the actual modeling terms here. So what we start with is actually a model that learned the exercise we just did. It is trained to say, is this pixel from the same place? And we use that model, it's a trained backbone model, to then I'll go through the steps in more detail. But this backbone model is trained on a massive amount of data. It's very easy to gather data that says, are two images from the same place? Because all of our remote sensing imagery is geo-referenced. So we can say, I sampled a pixel from this image versus this image over here, and I know they're different because they're from different places, or we're sampling from the same location. We then fine-tune that backbone, and I'm going to get, again, more into the details on this, but this fine-tuning stage helps us really calibrate our scores. And so if you saw the title of the talk, it's about weakly supervised video analysis. Here's the weakly bit. We used a very, very, very small number of annotated examples to calibrate these scores themselves, where we graded pixels on a 4-step scale from a fully occluded to fully clear and tuned those scores. We also used some synthesized examples. I'll get into those too. But again, this fine-tuning stage takes us from being able to tell if images are from the same place to being able to calibrate scores that are grading the atmospheric similarity, which is where the ASIM acronym comes from. It's an atmospheric similarity index metric. And then this ASIM model that we begin with then feeds into a larger QA model, what you would think of as the CloudScore Plus processor, where we again, use a larger body of images to then be able to grade the individual examples. And the output of this QA model is what we're surfacing as CloudScore Plus. That was a lot, top-level overview. Let's dig in a little bit more, but here we've got some visual examples to back up the points. So in our ASIM pre-training, so I was saying we have this model that's trained to say if two images are from the same place. The key here is that we give the model two different images. So we've got image A and image B. And we combine these pairs of images to train ASIM, which you can think of as a feature extractor. So it's a big deep learning model that we're going to end up using to kind of pre-process images we use in the larger QA model. We apply a bunch of different augmentations. So if we have image A and image B, one of the keys here is we actually mix up the pixels from both of them. So we can say, hey, we grabbed a pixel from B and a pixel from A, and we know that if those images were from the same place, we could call them same. But if they were from different places, we call them different. And if that's mixed up, and you can look here in this example, whether the pixels are true matches or not, we can then grade and score the similarity of those image pairs. We also do a bunch of augmentations, spectral rotation, which helps us augment the different channels of the imagery, so changing some of the channel values in the source imagery so the model learns to be robust to spectral differences, like when you saw those wetlands changing colors in the initial image examples. We do some resolution reduction. We've applied CloudScore Plus for Sentinel-2, but you could imagine if you wanted to apply the same approach to Landsat, whether or not the pixels are 10 meters or 30 meters, we want it to be robust to that. We do some deformation, so we woogle the images, and this accounts for geo-registration errors. Remember, we care a lot about similarity here. We didn't want our cloud detection modeling saying, hey, this road wasn't registered as well in the images that are being compared and flagging that as bad QA. And we also do some standard image rotations in general, just traditional computer vision where you're just rotating the images. Key here is we rotate both of them so we don't rotate image A but not image B. And all of this to say that we end up with a model that is robust to all sorts of changes and artifacts of things happening on the ground, but we're able to generate a prediction, so an actual score of whether these images are from the same place, and we can do this at scale. So we can generate an almost infinite number of these sorts of paired images where we match them and don't match them. And again, I like to show this as an example. So when we're saying, do the images match? Well, here's where semantics really make a difference. So if you see the pair of triangles and the pair of circles, well, those match in terms of shape, but the colors match in terms of they may be different shapes, but the same colors. This maps to the idea of we wanted to teach the model to ignore changes like what you're seeing here in this sequence, where if snow falls on the ground, well, that's not bad QA. That's not an atmospheric effect that you would want to detect with some sort of cloud and shadow detection approach, but you do want to be sensitive to white puffy clouds coming into the picture. So again, by training the model on saying all of these images are a match, we want those to be scored as having similar atmospheric conditions versus when there's an actual intrusion from a cloud or a shadow. Those are the differences we care about. And so I wanted to show this just for fun. If you want to see the guts of this feature extraction, if anyone's worked with deep learning networks, here's some of the actual features from one of our decimation stages. But here, maybe the fun thing to take away, where those blue circles are in our feature extraction actually correspond to a shadow on the ground. So we're looking at a pair of images, and then our atmospheric similarity score in this darker image at the corner, and you see that little lit up white area is actually a sneaky cloud shadow that gets in there. Really hard to see with human eyes, but our model was able to start to extract that. And so, again, remember I said we trained this big backbone on a whole bunch of examples. Well, we needed to give that backbone some concept kind of what these values mean and kind of rank them on a scale. So for the weakly supervised bit, we have a total of, would you believe it, 900 image pairs, of which only 512 had annotations, and of those annotations, they're not even the full image chips. So it's a very busy slide. We call this nightmare mode because it is some of the hardest examples we could find. Things like teeny tiny cloud shadows like what I just showed, little bits of cloud puff, changing fields where we wanted to make sure the model understood a field change should be treated as similar, a flood event should be similar, but a little tiny cloud shadow getting in there would be marked as different. So these all got marked up, and you can see the actual annotations in the primary colors, and to the left of each of those are a confidence score or an alpha channel, but this is the entirety of the supervision that went into the model. The other bit of not marked up, but way that we calibrated our cloud scores was using what we call the cloud artist. So look at these images. These look like Sentinel-2 images, right? Believable, maybe? If you're questioning it, might be because these are actually synthesized images. So I said cloud artist. We have simulated clouds and cloud shadows and applied those to Sentinel-2 images. Now, why did we do this? Well, we have our annotations, but to make a bigger training set, here we know the actual opacity values of what we generated, and so we can boost our training set by building in these additional synthetic images, which give us more examples to train on. And so between the combination of our human interpretations and our cloud artist scores, we end up with a fairly large training data set. And what comes out of this is what we call the ASIM score. You can think of it as sort of the cloud score plus precursor. Again, I'm going to pull all these back together in a couple of slides. But this ASIM score, again, atmospheric similarity index measure, is a per pixel score. If I give the model two images, it tells me at a per pixel level how estimated it thinks the similarity of those images are, and then we can aggregate that up and get a match score for the entire image. So if we take the minimum similarity across the whole image, we can say whether or not these two images have a similar atmospheric condition or they differ. And why this is important, because these ASIM scores, these scores that we generate for pairs of images, become the training examples or our way of mining training examples for the larger cloud score model. So the cloud score model, we take pairs of images and we sample, and we have some requirements. We needed to find locations for our training where we had at least one pair of clear reference images. So we took the ASIM, and we said, okay, remember, if we look at the min score, if we say that the min score is pretty low, that these images were graded overall as having mostly very similar pixels, I can say those are clear images. Why do clear images matter? Well, going back to the beginning example, that helps me determine whether or not something is different relative to this clear reference image. And then we also take a set of additional images. Here they're shown in blue boxes, but these are images that we want to use for grading, and we calculate the ASIM scores. You can see them kind of to the side and the right of each. Those are the training examples for CloudScore Plus. So the CloudScore Plus model is going to be given these examples where we have a known reference and we're able to compute the ASIM score relative to it. We've got the ASIM scores themselves, which are what we want the model to be able to reproduce. And we have this whole series of images. So again, going back to the title of the session, here's where the videos come in. What's a bunch of satellite acquisitions of the same place, but really just a movie. And so we treat them like a full time series. And in total, we were able to automate the processing of mining over 2.2 million of these examples. So we went from just a very small number of hand annotations, a bunch of creative strategies for making a giant training data set, and then we mined out a bunch of these video sequences. We also included information on terrain. So another big cause of shadows in imagery are terrain and other ground-based occlusions. So we wanted to have the model learn an understanding of that. We also had information with our examples. You'll see there how many images were in it, whether they fell into these different categories. So traditionally hard things that are confused with clouds and shadows. For example, bright targets like deserts and snow are often confused with clouds. Very dark things like topographic shadows, bodies of water are often confused with cloud shadows, and built targets are often committed as clouds or shadows. You kind of get a mashup of different things. So we specifically targeted regions of the world and sampled UTM zones that had high proportions of these land cover types. We drew all of these samples, and it gives us this giant training data set. So if I look at an example kind of in a prettier format here, when we're building the big CloudScore Plus model, remember I said the ASIM model needs 2 images. Has anyone ever tried to build a clear reference image or a median composite, any sort of mash the pixels together and get a perfectly clear look for a part of the world and not been able to do it? Raise your hand. Have you ever had just a holy image, no matter how hard you... Yeah, so there are places where I'm never going to be able to give a model a clear reference and something to compare it to. And that's why we needed this much larger model that is now able to understand that kind of feature extraction piece from the ASIM model. So how do I extract information from the image pairs that are relevant to detecting clouds and shadows? But now we need to apply that in a way that doesn't require knowing a clear reference. And that's where, again, the time series is coming in, because we use the series of images rather than just a pair to grade a single target image. And we needed those clear references. You may be saying, yeah, so you mined clear references. Why are you saying, well, what about when you don't have them? We need those for training. We need to be able to compare to a clear reference to be able to tell if the model is doing a good job grading things, but we don't assume that there will be a real clear reference when we go to run this model at inference time. For those in the room who are really into the deep learning side, we do have a model diagram here. I will say the really important things to take away is that we've got a single input image that goes into CloudScore Plus. We use that ASIM model to generate the features, so we apply it and get feature extractions for each of the history images, and then we use that history of images to essentially attend to. So we have a pooled attention layer that combines the properties of different images in the history. And really what this is doing, kind of in plain English, is creating a clear image to compare to. So if you don't have that clear image, the model is learning how to pay attention to different parts of the history of images in order to make a grade, that CloudScore Plus that we're surfacing in our image collection for each each new acquisition or each target image that we point the model at. And what I think is really cool is that our attention layer had 3 heads, so we can actually visualize the weights of the different images in the history as these sort of composite images. And you see here with the red, we're getting like a little bit of attention from image 6 and 7, this kind of mushy gray thing. Well, that doesn't look so clear. We suspect the model may do things like this when it's trying to think about, well, is it snow? Is it cloud? And being a little uncertain. The green one makes a lot more sense, at least to me, where it's saying, okay, well, if I pull a lot of pixels from 7 and 8, image 7 has a bunch of cloudy things in it. It's not really picking those pixels, but it's grabbing stuff from those clearer parts of 7 and 8 and a little bit from some of the other images to make this kind of clear. And the blue one, very similarly, it's pulling from some of the clearer portions, in this case, more from images 4 and 5 there. But that's kind of, again, very in the weeds on the actual functioning of the model. What the real goal is to take this history of images and then be able to reproduce the score, that ASIM score that we have. So we have that clear reference. We're able to run it through the ASIM model, get the score, use that as our target. And so we've trained this whole machine to essentially refine and better that original score for a pair of images. Now we run it for a single image, but a history of, they could be cloudy, they could be clear. We can pick any of the images, both in the history, and I say history, that really works mostly when we're moving forward as new images are acquired. When we're doing kind of backfill on our images, we actually can look in both directions, so we can pull comparable images going forward or back in time. And at the end of the day, those of you who are here, okay, what does this mean practically? Well, when we get to the end, our actual prediction, we get the Cloud Score Plus result. And what you can think of this as, going back to the original idea of, we have this theoretical now clear reference. Remember, there's places in the world I don't have a real clear reference. I only have this kind of synthesized reference that the model is making up as part of training. And so that comparison between a theoretical clear reference and how much of that is actually being occluded by clouds and shadows, Cloud Score Plus is almost like the alpha channel in between those. So if you've ever worked with a PNG where you get that kind of faded transparency effect, if I put a slider all the way towards give me clear surface, I'd get a Cloud Score of 1. So keep all the pixels, it's totally clear. If I start sliding that into the bad data side at a per pixel level, then I'm kind of tipping the balance into, well, it's partially occluded by a bright cloud or a shadow. I can see some of that surface through. And when I go all the way to 0, now it's fully cloud or dark shadow. I can't see anything from the surface. So if you're using Cloud Score Plus, that's maybe the biggest key take home of what this all means, is that we've got this slider between clear surface and not clear occlusion. And so here it is kind of in a more visual form, similar to what Rebecca showed in the keynote. So we can then take this continuous score, which is grading the occlusion of each pixel, and we can use that to create a mask. You could use it as a continuous score. I'll show you in the demo later at the end of the presentation what that looks like kind of in both directions. We've got an example here as well. But if we apply a threshold to this continuous score, the values that are greater than the threshold, 0.6 has worked generally pretty well, but I'll say it up front. This is something that's very tunable and will depend very much on your use case, your study area. You should experiment. We've tried everything, and Andrea will speak a little more to this, from 0.55 to 0.85 and gotten good results. But you can set a threshold. The values less than that threshold, again, closer to 0, are going to be things that you probably want to remove. Greater than that threshold, let's consider those clear. And we can kind of parse this image and factorize it into the atmospheric occluders, the bad QA, if you will, and the surface properties, the good QA. And that's maybe the big shift in thinking with Cloud Score Plus. Like I said earlier, most people are treating this as a segmentation or a classification problem. We're treating it as a QA grade. So even though it says cloud score, we're grading overall QA, how usable each individual pixel is. And if you want to learn more, read more, revisit anything I talked about in all the technical and mathematical details, we did have a conference paper at the Computer Vision and Pattern Recognition Conference in Vancouver back in June. And so that has a lot more examples. It's got more details on the model. If you'd like to read more, the link is in the slide deck. But for those of you who maybe care a little less about how we built it and more about how the heck are we going to use it, what even does it look like in Earth Engine, this is the section for you. So again, we are running our giant CloudScore Plus model for the Sentinel-2 archive. And when I say Sentinel-2, the images, the CloudScore Plus results are generated from the Sentinel-2 L1C collection. So we will have that whole history going back to the beginning of Sentinel-2 acquisitions. That said, just because we generate it on L1C, it works equally as well on L2A. So if you're working with surface reflectance, you can swap in either, this is a cloud mask or cloud shadow and other atmospheric occlusion detection that will be applicable to either. And we've been saying cloud score. Cloud score is actually a 2-band image in the collection that we're launching. And you have 2 different scores that you can choose from. So there is a band named CS, cloud score. This is the actual pixel quality score. And what you can think of this as being mostly related to the spectral distance. So I told you about that theoretical clear reference. So this is the prediction of how different is this individual pixel in the given Sentinel-2 image from that theoretical clear reference on a score of occluded to unoccluded. And one of the things I want to point out here is you'll notice kind of this purplish area, so that that kind of low-level haze or haloing around the clouds. And I'll show you the source image again here. So cloud score is sensitive to that like kind of thinner, hazier area around, whereas we also have the CS-CDF, or cumulative distribution function. So this kind of takes a step beyond cloud score itself, that raw like difference kind of value, and it gives us the value of the cumulative distribution function of the possible CS values given the estimated CS value. In other words, think of it more as like a likelihood of cloud. If you've worked with the original cloud score, simple cloud score algorithm, this is given a whole set of scores for a stack of images. Where do I think that score of the given image falls in that kind of range of possible values? And what I want you to notice when I flip back and forth, CS-CDF tends to give you this kind of tighter, neater boundary. It almost looks like a cloud mask. And so the threshold here, you might want to bring that threshold up, make it closer to 0.7 by 0.85 to capture kind of thin things along the edge. But if you really want kind of that high precision, you don't care so much about thin haze around clouds, this might be the better band for you. We've also found it a little bit more robust to some terrain artifacts and things like that. So experiment with both of them. We're very curious to hear which works well in which study areas, where you're finding one is preferable over others. And we're giving you both because we think both of them do different things for different use cases. And so just to flip through what this looks like, if I apply that standard threshold here, I'm using kind of 0.65, so a little bit more clear conservative. You can see that we're doing a pretty good job of masking all the clouds. And again, that difference of cloud score getting those kind of thinner kind of edges of things versus CDF is a little bit tighter and gives you a little bit more clear pixels at the same threshold. Again, thresholds being tunable. So we are launching an image collection where the cloud score images have these 2 bands. And as Rebecca mentioned, we have processed back to the beginning of 2022. So that's over 7.5 million Sentinel-2 assets. This has been a big lift. We're doing all the ML so that you don't have to. And this is currently available. I'll show you the collection ID in just a sec. But we also want to make sure you know we are working hard on backfilling the rest of it. So we intend to go back to the very beginning of that L1C archive, and we will be issuing some updates along the way. So stay tuned, and we'll keep everyone posted as there's more imagery available. If you haven't already, you can visit the CloudScore Plus catalog page. We have the image collection, Google CloudScore Plus V1, first version of the model, for S2 harmonized. And that's S2 harmonized as in the harmonized baselines of Sentinel. I know this gets a little confusing with HLS. This is not for HLS. This is just Sentinel, but it matches the ID of Copernicus S2 harmonized, since that's the images that you would want to work with. But again, yes, it does work for S2 harmonized and S2 SR harmonized, and that's all noted in the description there. There's also, I didn't show it in the slide deck, but there's band descriptions, image properties, the citation to the paper. So really everything you need is in that catalog page. And the other really exciting thing that we are very excited to announce is a new convenience function. So if you caught in the keynote, you may have heard CloudScore Plus, not only is it one score to capture all of these atmospheric artifacts, it's also a one-line join to now connect it to the source imagery. How many of you have ever had to use a join in making a cloud mask for Sentinel-2? Yeah, it's a lot of code, right? You got that big block, you've got to have your join object, you got to apply your join. And most of the time, what you really want is just to say, these bands should be added to this image. That is what linkCollection does. So it is a single line. It works on both EE images and EE image collections. You specify the source collection, the collection you want to join, which bands. It defaults to joining on the system index. So in the case of CloudScore Plus and the Sentinel collections, they both have the same system index, the same image ID. So it just works. And you're able to say pull over either just CS or CDF, or you could go the other way. You could take CloudScore and join Sentinel-2 to it. But what you end up with is, if you've ever worked with a virtual raster, it's kind of akin to that, where the image will have all of the added linked bands, and it will just function as if they were already in the same image collection. And so what this looks like in practice, rather than that big giant join and bunch of lines of code, I've got my variable here, linked collection, S2, linked collection, CS plus bands. That's it. And then I can proceed with a median composite. Here I've got a little function for doing some masking and the actual compositing happening at the bottom, but it's that simple. And this function, we're curious to see how you use it in other ways. It's not just for CloudScore Plus, but it's going to make the experience of using it so much better. So I've been doing a lot of talking and telling you about the model and the product. I want to hand it over to Andrea, who's going to tell us more about how she actually used it for a case study.
Thank you, Val. Isn't that impressive? Come on. All right. So yeah, I'm going to share a little bit about Servia Masonia project on land use and land cover classification using the CloudScore Plus product. So this is the area of interest. It is the province of Imbabura in Ecuador. And just for some context, so you know a little bit about this area, this province has a population of about 470,000 people. It has varying topography, as you can see here, a lot of areas, you know, high elevation areas, mountains. We have volcanoes that I'm going to point to in a second, and forests too here that are part of the Amazon biome. So we work with the province of Imbabura, and they want to, you know, monitor this region, map land use, land cover, not only for natural forest management, but also because this region has a lot of agricultural activities as well. So this is a collaboration between Servia Masonia with the local partner in Ecuador, Ecociencia, and also the government of Imbabura. And the idea was to develop a land use, land cover map for the year of 2019 as a pilot. And they wanted to do this because they wanted to improve at the regional level current existing land use, land cover maps that are on a national scale. And as you can imagine, we are in a tropical region. We get a lot of cloud cover throughout the year, and there's a limitation on using optical data for this purpose. These are some of the areas that I'll be highlighting in this presentation. So you hear me talk about Las Golondrinas, Volcano Cotacachi, Volcano Imbabura. Both are dormant, so they're inactive. And then the northern region and the southeastern region just so you know where they are located. And they are spread out across the province. So the goal here, as I mentioned, was to improve this land use land cover data. It currently relies on the national maps that are produced biannually by the Ministry of Environment. And they are great 30-meter resolution optical derived products, but the province is interested really in the finer scale, in the 10-meter resolution, and more accurate regional information as well. So we decided to have this pilot approach for the year of 2019, and they wanted us to use the same class schema that is used in the national maps. So as you can see here is a mix of forest cover and land use and land cover as well, which makes things a little bit more complicated, but we decided to tackle anyway. And the map you see here is the national 2018 classification. And as I mentioned, there is persistent cloud cover throughout the year. This map that you see there shows the number of consecutive days without data for 2019. And this is data from a recently published paper. I have links there to access that data set. And the real message here is that darker colors are areas with less data availability. And this is based both on Landsat and Sentinel-2. So we're basing our classification in Sentinel-2. So if you remove Landsat, you can think of these areas even with a more red color. So you can see, for some regions there, some areas it's really bad, right? We don't get a lot of consecutive days with data. And the GIF animation that you see there, that's from it's a time series of Sentinel-2 images for the year 2019 over the volcano Cotacachi. And as you can see, or may I say, you can barely see it, right? You cannot even see the crater. But the crater is not important, it's dormant, we don't care about that. But the area surrounding the volcano, the mountain, has a lot of important forest plantations that the province is interested in monitoring. This is another map just showing how bad cloud cover is. So this one shows the number of cloud cover free observations, again, both with Landsat and Sentinel-2 for the year of 2019. This has a reversed color schema, but the idea is the same. The more red color is worse, is like bad. So depending on the region that you are at, depending on the pixels you're looking at there, you can only have one or two images, clear images in the entire year. This GIF animation this time is from this region called Las Golondrinas, and it has lower elevation than the other areas of the province, which helps a little bit with what we are trying to do here. But as you can see, it has a lot of cloud cover. And this particular region has a lot of cropland, so it's important also for the province to monitor. So one of our, and by our I mean, from the surveyor side and the province of Imbabura side idea, the first idea was let's use synthetic aperture radar, right? Because it can penetrate through the clouds. And then we decided to do that, but also, it's important to say that not only use it, but couple it with the optical data because we know both of them have different advantages. So this is what a Sentinel-1 median composite for the year of 2019 looks like. As you can see, and I have mentioned, we have a lot of topography. That's really challenging working with the SAR data because you're going to have some shadows. You're going to have sides of the mountains more bright than it should be. And unfortunately, these are the ground range detected data. But fortunately, we can also apply a terrain normalization. So we have applied that according to literature to try to correct topographic effects there. And this is what it looks like. It's a little bit better. And you may not see in this image, but when you you zoom in, you can see that still there are a lot of voids that are from the correction, shadows and other artifacts that in the composite. So it's hard to work as well. So when I heard about CloudScore Plus through the GDE program, and I signed up to be one of the testers, and the first time I looked over the composites created for Imbabura, I was impressed. It was mind-blowing to see the results of CloudScore Plus output here. And I generated, again, composites for 2019. I used the median reducer. I've been using median reducer for all of the satellite inputs used here. And first, I started with the cloud score band with the threshold set to 0.6. And then I did some analysis, not only changing the threshold for CS band and the CDF band, but also comparing the two as well, using the same threshold for both. Just before I show the beautiful composite that was generated, this is a composite generated using just the quality assessment band. So that's the traditional approach that you see also, the developers page. This is what it looks like. You can see, there's a lot of issues with this composite, a lot of areas without data. You can still see a lot of clouds and cloud shadows, so it doesn't look great. Then Sentinel-2 Cloudless, which was already, a great improvement for composite. And just disclaimer, this is using Sentinel-2 Cloudless algorithm as is, so as it is provided in the developers page. I didn't try to change it in any way. And we can see it already improves a ton, but still has some issues with that composite. And then a lot of times, Val mentioned, you have to use the joins. A lot of times this would crash when using Nerf engine generating from the Sentinel-2 Cloudless algorithm. And this is the Cloud Score Plus result. And you say, oh, it still has some gaps there, but it is a huge improvement over the other two outputs. And the people from the government of the province of Imbabura were astonished when they saw this image from 2019. And I'm going to show more detailed example. This is one of my favorites. I think is one of Val's favorites as well. You can see that both the quality assessment and the Sentinel-2 Cloudless outputs miss the volcano, the creator of the volcano Cotacachi. And it seems that for Sentinel-2 Cloudless, the mountaintop is flagged as a cloud and not corrected by that cloud's displacement index. And in terms of classification, from the QA output, for example, because it still has a lot of cloud effects and cloud artifacts, these could yield in the classification errors for those specific pixels that are not being masked. So that's a big problem in terms of classification. This is another interesting example. This time it is over the volcano Imbabura, so it's the other volcano. You can see that both QA and the Sentinel-2 Cloudless outputs are missing some clouds there, so there still exist the clouds here. But for the Cloud Score Plus output, it masks pretty well, right? You don't see that same cloud that you see in the other images. And again, this could easily propagate through the classification errors. This is another example of Las Golondrinas. And again, Cloud Score Plus output looks like the big winner here. We have a lot of artifacts in the other two outputs. And in terms of classification, let's look at some classification results. We started with just classical random forest to serve as a baseline. And currently the model takes as input spectral bands from Sentinel-2, planet NICFI mosaics, and also backscatter information from Sentinel-1, the terrain normalized composite. So we took all of that, threw in a random forest model, and that's the current result we see as of now for the province. You may not remember what the national map for 2018 looked like, but this is a zoomed in area. We showed this to the government. They gave us feedback of this map, and they said obviously it's more refined because it's at 10-meter resolution, the national map they're generating using Landsat data. But also overall, they said a lot of pixels were not with the class they were supposed to be, and now with this product, it is much better. So here on the left side, you see the Cloud Score Plus 2019 classification. The middle is the 2018 National New Zealand cover map, and then the satellite image on the right. In terms of accuracy metrics, so the classification using Cloud Score Plus output show higher overall accuracy. So I basically just took the composite and was swapping the Sentinel-2 output to test how the accuracy changed. And then it may not look like a ton, but increased 2% compared to the other products. You may think Andrea doesn't know how to model because those overall accuracy results suck. But think of it, just by changing the cloud masking approach, you already improved 2%. Imagine, we're working to get more training data. The points we use to validate the data, we are not so sure about the quality there, so we're going to do a quality assessment, quality control. So, this is not related to CloudScore Plus. This is something that we work on the model, but just by changing the Sentinel-2 product being used, it already improved 2%. When looking to specific classes, so produces and uses accuracy for specific classes, we also had some interesting results, interesting improvements. What you see here is a table. It's very busy, but it is the accuracy in percentage for each class and using the different Sentinel-2 outputs. So to focus here, the red color is where CloudScore Plus performed worse than the other two products. In yellow color, performed better than at least one of the two outputs. And in green color, performed better than both the other two outputs. And we have more green than yellow and red, you can count to see. And then what was more astonishing, I think, was the improvement seen with the Bearland class that is highlighted there in a green box. So with the user's accuracy, there is a 6% difference compared to the quality assessment band and 11% difference compared to the Sentinel-2 Cloudless. And producers, we have 15% difference compared to the quality assessment band and then 21% difference compared to Sentinel-2 Cloudless. And you may ask, Andrea, why is this happening? I don't know yet. I have to look at the points, the specific points we use to validate to see exactly what's going on. And I'm really curious to see what's going on there. After getting these preliminary results, I decided to test a little bit the threshold. And as you can see here, I started with 0.4, 0.5, 0.6, which was the standard one, and 0.7. And then as you expect, lower threshold, more cloud artifacts in the composite, higher threshold, too much masking, but then you might start losing important information. So you really need to test it to see for your specific region what works out. In my case, I think, the 0.6, after this, I decided to test the 0.55 as well. But before that, this is another example, but for the northern region. And again, the higher the threshold, you start getting the information there, which might be useful information. So I took a look at 0.55, 0.5, and 0.6. And maybe for one particular area, the 0.55 looks better than the other two, but then I would move to another area. It seemed like 0.6 was doing better, but that didn't make too much of a difference for this case. So I decided to stick with the 0.6 threshold. Then I looked into the composite output using the CDF band this time and the same 0.6 threshold and compared it with the CS-generated composite. And you can see, you might not be able to see too much, but what I gathered from this was that, there was a 180% difference of max pixels. So the CS band was masking a lot more pixels than the CDF. But when you look at the pixels that are not being masked by the CDF band, they still had some cloud artifacts. And it is really what Val was explaining that, with the CS band, you can capture more the edge of the cloud, where with the CDF, you just have that thick cut of the cloud. And for most of the regions, I found out that the CS band was working better than the CDF band. So I think, again, it depends. This is for this particular region. You need to think about, the last masked pixels versus the quality of the unmasked pixels. But overall, the CS band seemed to do a better job for the whole area, except for one region. There was one region that it was the opposite, and that was the southeastern region. But that's the only part of the Imbabura province where we get extreme cloud cover with very higher elevation. So for that extreme case, the CDF band seemed to do a better job. And then I think that was also in agreement with other testers that were testing this product over very high elevation and a lot of cloud cover. And that's it.
Want to step for a second? All right, before we jump into hands-on demos, we've been talking a lot, and I imagine there might be some questions. Does anyone have any questions about everything you've seen so far before we start playing with the actual results? I've got some cool demos to show us individual images, median composites, but happy to take a pause here. Yeah. Can we get a microphone? Thank you.
So it's giving a score on basically like quality of the pixel, right? Regardless of seasonality, right? It doesn't have a sense of seasonality.
Yes, that's that semantics matter bit.
Right.
We have trained that model to ignore seasonal changes, field changes, snow changes,
Right, so
and
a snowy clear picture is just as good as a grassy clear picture.
exactly, yeah. And the idea here, just to build off that, like we've factored out like atmospheric effects and ground effects. So you could imagine, hey, I want to get rid of snow in my images. You might run a secondary classification where snow can now actually be a class because it's not going to be confused with cloud.
But isn't it also building internally like this theoretical cloudless picture?
Yes.
So how can it do that if there's no seasonality? Like there's no such thing, right? Like what does that picture look like if you're in a place that is snowy sometime or green sometime and bare sometime? And could that have some relation to what you're seeing with the effect on bare ground working better as a classification,
And a really good point, and something I didn't actually get into when I was talking about when we draw our samples, we actually constrain the way we draw those samples, that big grid of images, to, we call them octants. They're not really seasoned. We divide the year into eighths, but we do consider that within that period that the seasonality should be fairly consistent. So you won't see changes for like the slight transitions in phenology, but the model does have a sense of consistency within a season. And when we're drawing that history or even like both sides of the images, we still stick to that octant idea. So we only use images in the query that are from around the same time, so the model doesn't get tripped up on really major changes, which allows us to keep snowy pixels, keep seasonal greening and browning, and not mask that as bad QA. That said, we do see kind of little bumps in QA scores. Like if you're looking at fields, if you're looking at deciduous forest, you might see a slightly elevated value. But when you go to make a mask out of it, that should all just come out in the wash.
Cool, thank you.
Yeah, good question.
Hi, you said you applied pixel reductions, so this model can be applied to Landsat?
Well, in theory, it could be. We've done some very preliminary tests, and we would love to hear if that's something people would like to see. Keep that demand signal, and we'll see if we can get it in the roadmap. It has not yet been generated, other than just a few cool test examples to see, will it work?
All right, so I think you answered the other question, which is, can it go in the other direction? So like planet imagery, higher resolution.
So it's interesting. If we were to go in the other direction, so no matter what we've been testing on, we always consider Sentinel-2 as our history of images, that sample of, or I should say query of images, but the set that we're comparing to. And so if we were to point it at something higher resolution, we would end up with a lower resolution output. So like I wouldn't be making a Planet Cloud Score Plus at Planet resolution. It would probably still be at Sentinel resolution. But the idea behind the whole process was that it would be a generic processor that could, in theory, work for coarser, finer, just optical images in general, dealt with through all those augmentations.
Okay, any plans to tweak it for higher resolution?
Like I said, demand signal is everything here. For now, we're just piloting the Sentinel-2 launch, but if it's really well received, if you guys want to see more, let us know.
Thank you for the presentation. So as I understand it, this Cloud Score Plus is for all types of occlusions, which means like clouds, cloud shadows, even like fog, I would assume.
Yep.
Anything in the atmosphere, anything happening in the atmosphere, right?
Yeah.
Do you know of a way, let's say I actually want to know how much cloud there is or if a pixel is cloudy. I'm assuming there's a threshold, but it would be regional. Do you have any thoughts on that, or have you considered that?
Yes, and this goes back to the question about factorizing the image, right? If you actually took the portion of the image that is scored as bad QA and then classified that as cloud or shadow, or maybe cloud, shadow, fog. You want to add all the labels, thin cloud, cirrus cloud. You could use CloudScore to help you figure out which portion to apply that to. So we didn't add any semantic judgment on what was the bad QA, but by taking out, like, now you're not going to confuse cloud and snow or shadow and water, you should be able to do a secondary classification. It's weird to think about, because usually we think about classifying the ground, but you could basically mask the clear pixels and classify the bad QA into subtypes.
Thank you.
Yeah, and if anyone does that, I would love to see it. I have some training data I might try this with, but that would be a fun exercise.
So thank you very much for your presentation. It was really great. I'm wondering, so in your slides, we have seen so many amazing examples of how the CloudScore work on land surface and also some surface water like lakes. But I'm wondering, have you already have examples on coastal water or over the oceans, for example? How good is it at detecting the cloud shadows? Because, for example, for other processors, they usually make the misclassification there.
Yeah, so we worked really hard on trying to get shadows over water, and there are places we do really well with it, and sometimes, water is dark, shadows over water are even darker, and so it is definitely one of the more challenging places to work. I would love to hear any feedback on if you've got specific coastal areas that you're looking at and if we're getting things well or not. We tend not to lose bright beaches, things like that. We do mask, so here's an interesting conundrum in the philosophical challenges of bad QA. When you get reflections of clouds in water, are they good QA or bad QA? They look like clouds, they're bright, they're not really representative of the water property. We tend to flag those as bad QA. So often when we're seeing lost pixels in big bodies of water, it's because we're actually getting enough of a reflection of the cloud in the water that the algorithm's like, well, it looks like a cloud to me. I've only got this 2D image. So I guess long way to say it depends on things like the reflection, the sun glint also tends to get picked up as bad. But yeah, that is an area I'd love to hear more feedback on whether it's working as intended or not.
Okay, thank you so much.
Yeah. You've got one more question and then we can jump in.
Hey, really excited. I tested this on some of my project. It works really well compared to the Sentinel-2 SR, cloudless, and other algorithms. It picks up the bright, a lot of the other algorithms get confused with the bright buildings as clouds, and this works really well. So great work. And a small piece of feedback, when I was trying to use this in the data catalog example, the example that's there, it's not useful for applying it to the data. So it'll be nice to have your script, what you showed in the catalog example, so that people can start applying it.
And it is an awesome point. So interesting, just fun fact. So in the data catalog, our code snippets are often for just the collection they're applying to. We went back and forth a bit. It's like, do you want to have to link to Sentinel-2 in order to make use with the Landsat and the Sentinel QA bands? They're already in the image, so you're still just on one collection. And we were questioning the interdependency if you need Sentinel-2 to use CloudScore Plus. So point heard, and we can definitely revisit the snippet. The good news is we are in the process of adding an example to the cloud and shadow masking section of the example scripts in the code editor that is very close to the example that I was showing on the slides and linked here. So that will be accessible as a small workflow, just like we have the ones for S2 Cloudless and QA already. So that'll be in there. And if we really want to see it in the code snippet, I definitely think that's something we could take that feedback on.
Thank you.
But yeah, great point. Okay, so thank you so much, Andrea, also just for going through all of that work to look at the different options. And I hope to see a lot more case studies where y'all are telling us what's working, what's not, and seeing those beautiful pictures. So in the time that we have left, I wanted to get into a couple of the tools. If you came to the demo booth yesterday, I did promise there would be links to these. So the first tool here, if you want to get in the hands-on portion, actually look at some images, is what we call our CS Plus Collection Explorer. So this is the place to go when you're first getting started and you want to figure out, do I want CS? Do I want CS CDF? What threshold should I be setting? Like, what am I looking at for my study area? And so I'll pop into the tool in a second, but really the goal here is to just explore the CS collection and how it applies to the source Sentinel-2 images. You're going to be looking at single date results. We've got a time slider so that you can page through. You'll see the big acquisition strips from the actual Sentinel paths there, and you are able to apply. There's a little pull down for whether you want to use CS or CDF as a binary mask band. We can also look at how it applies as a continuous. So some of you may be working with other deep learning models or models that can take weights. You may not even want to just say good data, bad data. You may want to say downweight things that are scored as pretty bad QA. So there's a couple different options in the layers list. And so here's that link really big. So we're in Earth Engine AI, projects, Earth Engine app view. I'll give you a second to type it. Or if you've got the deck from the short link over there, you can just click. And this is the CloudScore Plus Collection Explorer. And we'll see if I'm able to switch over to another tab. Am I able to get to a different tab on my browser here? Sorry about this. Hopefully, if everyone has a chance, let me go back. Sorry about that. Yeah. Is there any way I can present this one instead? Hold on. Awesome. Amazing, thank you. Yay, on the fly tech support. So, all right, here we go live. And you can see we've got imagery from the 9th. So we're usually around 24 to 48 hours behind the latest Sentinel-2 acquisition, but those results are coming in near real time. So here we can see, again, those Sentinel-2 acquisitions. If you wanted to change the date, you can use the date slider and kind of page back through for your study area here. It's a little lag. And if you want to get in there and really look at how well this is performing for different types of clouds, I can look at this guy, which is a bit of a mix of those really big opaque clouds and a little bit of thinner cloud. And I might want to do something like, what happens if I just stick with a 0.65 threshold, but I use CDF instead? We can start to see there's some kind of hazy stuff peeking through in the cracks. If I maybe wanted to make sure that I was masking those too, I could turn up the threshold. Remember, what's above that threshold on the high end is what we're going to call clear. It's closer to 1. If it's below that threshold, it's going to be masked as a 0. And you can see I start to see that kind of purple colorized. This is just the score values colorized. I also want to call out in this tool in the layers list here. So what we're looking at is this colorized QA. I could also look at what this looks like as a mask. So to do that, I can turn off the source image here and just look at the good QA. So if I put the good QA, and let's let that load with the colorized, you can see if that was just creating a mask, this is what would be left over. And if I wanted to, go back down to that 0.6 or 0.65 threshold, let's see what would happen if we went even a little lower. Now we've got a little bit more haze creeping in. But yeah, we can adjust the different thresholds. We can change the bands. I'll show you another fun trick. I mentioned that it is a continuous score. So this is where if we apply the mask as an actual hard cutoff. So I basically say everything below 0.6, I'm going to just say is bad data. Well, what if instead I just, instead of making a threshold, did what I was saying before and weighted the observations? If you've never done this before, you can actually pass a continuous value to the update mask function in Earth Engine, and it will adjust the transparency as opposed to just a 0, 1 on-off for the pixels. So you're getting kind of that grayish effect. That's because the areas that are really dark have 0 values. They're actually being closer to totally zeroed out. Those kind of grayish areas are in these transitional zones, and so you're getting kind of a partial mask. And maybe a little less fun for the good QA unless you're running a model, but I also, to the point about could you go and classify clouds versus shadows, well, here's if you flipped that, and instead you're applying that inverted mask to create where we've zeroed out or masked down the good QA, and we're only looking at bad QA. The shadows are a little hard to see because of the dark background. You can switch this to the map so we can see them a little clearer, but there you go. You could imagine if you ran a classification on this, you could probably do a pretty good job differentiating between dark things being shadows and bright things being clouds. When you get into the situation where you've got shadows from other clouds on top of clouds, that's where it is a little trickier, but again, interesting use cases. So this tool is really there to help you when you're getting started. You just want to know how it's working, making examples like what Andrea was showing, where you're playing with some of the thresholds, but instead of in the median composite space, you're looking at single images. You can also track what's in the collection, so you'll see the full availability, what's available in near real time. And so really, again, this is the Explorer tool. All right. That said, while this really showcases all of the actual CloudScore Plus results here, the other tool that we created is the one we use to make all of the median composites. So this is, instead of our CloudScore Plus collection explorer, we've got the CloudScore Plus clear composite tool. And let me flip back over to my slides here. So this tool, same start of the URL, but instead we've got the CloudScore Plus composite tool, is doing just that. So we've again got a slider. This time, instead of setting which image we want to look at in that single date sense, we are getting the start of an image composite. So you use the slider to say, I want my composite to start on this specific date. And then we have the option to change the composite period. And so we can change it to, we've got a bunch of different options. There's 5-day, 30-day, 60-day, 90-day, 180, and 1 year. You can choose, again, from whether you want to use CS or CDF for masking and what thresholds you want to make that mask. Here, it's just the binary mask, but if I flip on over to this tool, I already loaded it in the other tabs. We'll go back there. You'll be able to see that beautiful, clear Western US composite. And I think the interplay between the two, again, getting a sense of what's being masked at different thresholds, then bringing it over here, applying your learnings from the single image to make these composites, or just adjusting these thresholds to visualize imagery for different places. I hope you'll have a lot of fun playing around, looking at beautiful images. The last thing I'll point out, we got a lot of questions demoing last night. Can you export the images? Not from the apps themselves. It's always challenging. The median composite code and the snippet that'll show up in the code editor will help you do that, and you can add an export function. But one neat thing about both of the apps I just showed is they save their state in the URL. So if I copy this whole URL, it knows where the map is centered, it knows your viewport, your zoom level, all of the settings. So if you wanted to share just this app view with a colleague, with a collaborator, you can copy that whole big long URL. It's got a lot in it, but it it'll take them exactly to this, and you'll not just have a static, pretty picture, but an interactive map that they can look at. So I hope these will be helpful as you get started in your explorations. We are just about out of time. In my last minute here, I do want to thank the whole MLDP team. So I've got Wanda and William and Chris, who worked on the project in the past, and Sean and Ollie in the back, who have helped manage this whole effort, without which this would not have been possible. So if you've got more questions, we're around the next couple of days, or next day, only one day left. But yeah, thank you for being here, and happy clear imaging.